This is your lecture video for the second week of remote learning for regular chemistry. We are on page 7 of the notes on the challenge problem. So I'm going to go over a few notes for you, and got a couple puzzlers too. So anytime you need to stop the video, just please do so. And here we go. All right, here's a puzzler from Lucas. Give that a try. Here's one more. I'll tell you the answer to the puzzler at the end of this video. All right, so for this challenge problem, you've got a reaction happening. Zinc reacted with hydrochloric acid to produce hydrogen gas and zinc chloride. So please take a moment and balance this equation. The chemical formula for hydrochloric acid is HCl. So pause the video and solve. Go ahead and solve the next part too. All right, here's the answer for the balanced equation. If we look at the next part, we can see that we have several variables. We're trying to find mass of hydrochloric acid. We have volume of hydrogen gas, and we have standard temperature and pressure. Okay, so there's some values. You could also use atmospheres here if you wanted to for pressure. Okay, if we solve that, we're going to end up with moles. So I plugged it into PV equals nRT. Now, there is a shortcut. You could also just do 2 liters divided by 22.4, which also gives you moles of hydrogen gas. That's a shortcut. So because we know that it's at STP, we can use 22.4. Okay, now we're not done with this problem. What we solved for here is moles of hydrogen. We're asked to find mass of hydrochloric acid. So we're going to do a little stoichiometry. We're going to take our answer from earlier, change from moles of H2 to moles of HCl. So that cancels out our moles of H2. We get moles of HCl. We're going to multiply by the molar mass of HCl. That's going to get us to grams of HCl. All right, so that's it for the problem-solving part of this unit. You just need a lot of practice with this. Just a few last little bits about the ideal gas law. We've been operating under the assumption that the gases are going to behave ideally. They're going to be like small spheres. They're not going to repel or attract each other, and that the collisions are perfectly elastic, so no energy is lost as they're bouncing around. Okay, but it turns out, I'll answer this for you. Ideal gases don't actually exist. Okay, so if we look at this graph, which you have in the notes, this dotted line in the middle represents an ideal gas. So the pressure at different temperatures, over different ratios of PV over RT, we would expect this to be 1, right? PV equals nRT, so the N would be 1 here. At different pressures, we would expect that ratio to stay the same, but we can see that in the graph it doesn't. None of these gases represented here are ideal, even H2. So gases don't behave ideally, okay, especially at high pressures. Okay, because real gases do have volume, so we know that they bounce around like this. We know that they're very small compared to the amount of space, but they really do take up some space. Okay, real gases also attract and repel each other. So if you think of water molecules, there's a negative end and a positive end, and they do repel and attract each other. Okay, therefore, real gases do not behave ideally. So, you know, we can predict the gas pressures and temperatures and volumes, etc. But in real life, if we have really high pressures or really low temperatures, these values get less accurate. Okay, so I'd like you to try the review problems on pages 8, 9, and 10. I will show you the answers shortly. So please do those, and pause the video and do those at least on pages 8. All right, here they are. Here's the answers. Okay, so for the first one, you should get 405 kPa. Again, please pause the video if you need more time. For the next one, you should get 22.4 liters. You'll notice that all of these values are actually STP. So 0 Celsius, 1 atmosphere. Oh, this should be superscript here. Is it worth me fixing this right now? Let's do it. So because it's at STP and it's 1 mole, then the volume is going to be 22.4 liters. Okay, wood volume, 30 liters. All right, and then lastly for this one, again, we know it's STP, so 45.1 liters divided by 22.4 per mole times Avogadro's number, and you get this 1.21 times 10 to the 24 molecules of F2. This is just mole highway. Now, if you wanted to, you could also do PV equals nRT. You would solve for the number of moles. P would be 1 atmosphere. T would be 273. The R value would be 0.0821. You solve for moles and then multiply by the number of molecules per mole. That should get you the same answer. Okay, for the remainder of the problems on page 8 and 9, I'll send you a separate video.